Okay, today we're going to be talking about internal resistance and EMF. So previously we said that every component in a circuit has resistance. This includes the power source, whether that be a power pack or a battery, that will have some resistance. So far we've ignored the resistance of the power source because it's very small. However, if the circuit is low resistance, then calculations need to take internal resistance into account. So this internal resistance is the resistance of the power source. So typically it would be around about 1 ohm, maybe just less than an ohm. So if you build a circuit and that circuit has a very low resistance, round about an ohm, or maybe just a tiny bit more than an ohm, you need to then consider the internal resistance of the power supply in your calculations. Now let's look at what this looks like in a diagram. So here's our battery, and we can draw a little dotted box round it to show that this resistor is actually the internal resistance of the power supply, and we give this internal resistance the symbol little r to be the internal resistance, and it's usually between 1 to 2 ohms. So firstly we need to analyse the load. So this term load is the overall resistance of our circuit. Analyse the load of any components and potential impact. Now let's draw a simple circuit just to show how our little battery and our internal resistance look like in that circuit. So here is our internal resistor, here is our battery. Now we just have a normal resistor here, and we can have a voltmeter to measure voltage. So this is big R, this is our little r, and then we draw our little box round our battery pack. Now what we can think about this is equivalent to a kind of almost like a potential. What we've been looking at is potential dividers. So we have our battery, and oops, not drawn that line properly. Here's our resistor R, and we still have our voltmeter around it to measure its potential. Now here's our little r here, and now we're going to so So just kind of extrapolated this over here. So this is looks like the potential dividers we've been looking at. Now this is interesting, this little setup here is actually interesting because when we come to actually measure the internal resistance and investigate this more fully, we actually use a variable resistor, and we can use the equation for a potential divider to find little r. Now power supplies, so what does a power supply do? A power supply, regardless of what that power supply is, supplies energy. Kind of obvious. And it does so by changing some form of energy to another. So in a battery, you've got chemical energy being turned into electrical energy. And obviously, well, our mains power supply, take it back to the power station, you've got some kind of mechanical work being done to produce electrical work. So we define the total electrical energy supplied to the charges as the electromotive force, or EMF, and sometimes we'll just write it as E, big E, and it's measured in volts. Now, it's really important that you understand that this is not a force. It's not like one of Newton's forces. It's measured in volts, and it's the energy that's supplied to the charges. This term, electromotive force, is a historical term, and it's one of these, again, these kind of conventions that have been followed its way down through physics, which is a bit unfortunate because it does not give a proper understanding as to what's happening, a bit like the convention of what way current goes around a circuit. So we're stuck with the term electromotive force, but it's actually the electrical energy supplied to the charges. So we can now think of our battery here as having a value E of electromotive force, and we can actually put a wee voltmeter round here as well, and we can call this the load resistance of our circuit, and we can put an ammeter in here to measure the current. Now the potential across the internal resistance can be calculated using Ohm's law. So the potential across internal resistance can be found using Ohm's law as the current times I. And the potential across the load resistance is equal to I times R load. Now the EMF across the battery is the total of the potential across the internal resistance and the load resistance. So the EMF is equal to I R load plus I little r. Or we can rearrange that as E equals I times R load plus little r. So you can see that if this little equation here really makes it obvious the kind of situations where we need to consider the internal resistance. When if you've got a massive resistance of say 200 ohms and you only have like one ohm internal resistance, you don't need to worry about it. But when these are very similar, that is when you need to worry about it. So the potential across the load resistor is the same as the potential we use to measure across the battery when in most of the instances that we've already had. So this here, this the current times R load is what you'd have if say you measured the voltage over here. You would have V terminal potential. So this is terminal potential. And it's equal to IR load. So this, I'm running out of space. I'm going to do it up here because I want to keep it on the same screen. So we can think of this I little r as like almost like a loss potential. So we can think of it as E equal to V terminal potential difference plus V lost. And it's most often written as V terminal plus I current times the internal resistance. So let's look at how we would measure the EMF and R. So we would set up, let's just draw a little dotted line, bring this in. Here's our internal resistance R. And then we'd have a variable resistor, big R. We'd have our ammeter. This is our EMF. And we also need a voltmeter here. And so what we do is we take multiple measurements using the circuit at different values of R, and then we get a table of results for the current, and then we use, so we would have our table for current, and then our terminal V terminal potential difference, which is the same as IR load, which is the value we get here, and we get all these numbers, and then we would draw a graph. And so this is our current, and this is our terminal potential. And it's in volts. And we would get different values, and you see they're going to make a kind of straight line, and then you would, I'll get a different colour actually, you would then join them together in the line of best fit. And you would extrapolate back to the y-axis. So this shows that as the current increases, the terminal potential difference decreases. Now the extension of the graph to here, this shows what the EMF, this is as if there would be no current flowing through the circuit, and so the voltage would be the EMF, and we're able to make that reading. So the more values you take for your current, the better the fit for the straight line graph you get to here. Now, we know that E equals VT, terminal potential difference, plus IR. If we rearrange that, so we've got V TPD is going to be equal to E minus IR, and we'll just put this way around, so minus IR plus E. This looks very much like our equation for a straight line, where C is our E, so this is the point where it cuts with the y-axis, and because that's when the current is 0, so this would be E, and therefore our I is our X, so R is the gradient of our line. And you can choose different values to be able to work that out. So I hope that makes sense.